Ok.
Salut,
Ça va bonsoir à tous. Donc, je m'appelle Igor Caron.
Je m'appelle Franck Bardol.
Je m'appelle Jacqueline Forien.
Donc, vous venez au 99e meet-up. Jean, où es-tu? Jean, tu viens? Jean est un nouveau membre de l'équipe organisatrice.
Je m'appelle Jean.
Ok, merci Jean. Ok, donc c'est le 99e meet-up du Paris Machine Learning Meetup, 6e saison. Donc on peut sortir les statistiques, mais c'est un des plus grands meet-up du monde, qui est ici à Paris, qui montre simplement qu'il y a beaucoup de dynamisme en fait sur toutes ces questions. Et on est donc content d'avoir les meilleurs speakers qu'on puisse avoir à Paris, qui seront parmi les meilleurs au monde. Donc ce soir, on aura 3 talks plutôt que 4. Enfin, 3 émis. On aura une présentation de Samsung, on aura Denis qui nous parlera de conscience, consciousness, c'est pas comme ça se dit ici, c'est conscience. Si, voilà, consciousness.
Les troubles de conscience.
Les troubles de la conscience, ouais. D'accord, ok. Comment est-ce qu'on fait apprendre une machine comme un gamin avec Pierre derrière. Et Isaac Grant nous parlera en fait de tout ce qui est analytics sur du code qui est large scale. Donc, merci à tous les speakers d'être venus. Merci à vous d'être venus. On commence maintenant. Le prochain meet-up sera en janvier. Non, en décembre, le 12 décembre. Voilà, c'est ça. Ce sera le 100e. Et voilà, donc on ne sait pas ce qu'on va faire pendant le 100e. Mais si vous avez des idées de présentation, des idées de projets que vous voulez présenter à la communauté, n'hésitez pas en fait, à nous contacter à la fin du meet-up ou remplir le formulaire.
Et puis même des idées, même plus largement, d'événements, enfin je veux dire, du style, là, vous pourriez faire ci, mais aussi vous pourriez faire ça, voilà, ce genre de truc.
Oui, parce qu'en fait, on n'a rien à faire pendant le reste de la journée. Donc, on n'est pas sous l'eau de tout, en fait.
Pas du tout.
C'est pas du tout une organisation totalement chaotique. Donc, tout, voilà, on peut faire tout ce que vous demandez, bien sûr, puisqu'on ne fait rien pendant la journée. Et donc, voilà. Donc, merci à Samsung de nous avoir accueillis. Gilles, tu vas être le premier à présenter. Donc, Gilles Mazar est un data scientist à AI Samsung Lab. Je ne sais pas comment ça s'appelle, mais tu vas nous le dire correctement. Et puis, voilà, c'est ton show. Okay.
Bonjour.
Et tu te mets devant la...
Je me mets devant.
Ouais, parce qu'il y a un streaming qui se passe. Voilà.
Bonjour. Donc, d'abord, je vous souhaite la bienvenue à tous ici, dans nos nouveaux bureaux à Samsung. D'abord, quelques mots juste pour expliquer. Donc, vous n'êtes pas là évidemment pour entendre un truc sur Samsung, mais plutôt pour écouter les speakers, donc je vais faire très vite. Donc, qui on est? On fait partie du groupe Samsung Electronics, c'est plus exactement une entité qui s'appelle le Samsung Strategy and Innovation Center, qui a été créé par Samsung pour promouvoir l'innovation. Ce groupe-là est basé dans la Silicon Valley, à San Jose, aux États-Unis. Et nous avons une entité évidemment en Corée, à Séoul, une entité en Israël, à Tel Aviv, et enfin, depuis 6 mois, à Paris, en France. Donc on est très content d'avoir cette entité qui est l'entité européenne, il faut le dire. Et nous avons 3 activités principales. Donc une première activité qui est la R&D, qui j'imagine vous intéresse, qui s'appelle le AI Lab, c'est le groupe que je dirige. Donc on travaille sur de l'IA appliquée. Donc sur plusieurs domaines, l'IoT, les objets connectés, donc, je pense que vous imaginez qu'avec Samsung on peut s'amuser, on a beaucoup d'objets. On travaille aussi sur l'automotive, donc l'automobile et plus exactement les véhicules autonomes en général. Donc on a pas mal d'activités là-dessus aussi, et la santé numérique. Voilà, c'est les 3 grands domaines sur lesquels nous travaillons. En termes de technique, ça veut dire machine learning sur big data, deep learning, ça veut dire computer vision, natural language processing. Bien sûr, pas mal de techno. Aujourd'hui, on a 25 ingénieurs, bientôt 30 d'ici la fin de l'année, et on est en pleine croissance. Évidemment, on embauche, donc n'hésitez pas. Vous avez mon email direct là-dessus. On a aussi une activité d'investissement qui est à travers le fonds qui s'appelle le Samsung Catalyst Fund, qui est un des fonds de Samsung, et à travers Nicolas Autrey qui est dans la salle. Donc, si vous avez des velléités, n'hésitez pas. Et enfin, une dernière activité qui est Corporate Development, qui est dirigée par Roberto Moro, qui est au fond de la salle. N'hésitez pas à venir nous voir à la fin du meet-up pour discuter avec nous. Vous verrez des gens qui ont des petits des petits badges Samsung. Vous pouvez aller les voir pour poser des questions sur ce qu'on fait ici. Voilà, je vous souhaite un très bon meet-up et je passe la parole au speaker.
Merci. Pierre-Yves, t'es le prochain.
Thank you very much. Hello to everyone. Just a first question. Are there a number of people here who don't speak French at all? Okay, I'll speak English. That was a question from the organizers, whether I could speak French.
Right. So if you want to do this, at least your presentation.
Yeah, okay.
Be in front of the
In front of the camera.
Yeah.
Okay.
Franck. Est-ce que ça va ta batterie? Il faut appuyer sur le...
C'est à 47%.
Ouais, c'est bon.
On va faire le truc à chaque fois.
Pierre-Yves, tu peux commencer à te présenter.
Yeah, so thank you very much for inviting me to speak in this at this opportunity. So I'm a research director at INRIA, which is a French National Institute of Research in Computer Sciences and Applied Mathematics. For those who don't know, it's actually the biggest public research institute in computer sciences in Europe. It has more than 3,000 researchers. And I head a lab at INRIA Bordeaux and with a branch at ETSTA Paris in Paris. And our main topic of research is to try to understand the fundamental mechanisms that enable humans and machines to learn autonomously repertoires of skills. So it's a relatively fundamental kind of research, but as you'll see at the end, we also work on a number of applications which have relatively high societal implications, such as education. Okay, so let's talk about AI. So it's a bit difficult to talk about AI without remembering some of the hype results that we've been seeing in the recent years. And especially today, I'm going to talk about the special kinds of artificial intelligence, which is about how a machine can learn how to act in the real world, how to learn skills, how to solve problems. So, for example, I'm not going to talk at all about perceptual intelligence, like, for example, how a machine can recognize a cat in an image. It's really about the problem, for example, how can a machine learn how to develop skills in the domain of video games, or here learning to play games such as Go. And there were indeed very impressive results by teams, for example, by Google DeepMind, that showed how a machine could learn from scratch, from only perceiving pixels, how to solve a number of video games, and more recently, how to learn to beat even the best players in the world at the game of Go, which is very impressive because it's way more difficult than the game of chess. But beyond these impressive results, we've also heard in the news in many places that those machines were close to reach, or maybe even sometimes we heard they had reached superhuman intelligence. I guess any more than 5 minutes thinking about that enables you to understand that it's wrong, it's completely false. But it's useful to actually try to see in details why it's completely wrong to think that this kind of result is anywhere close to human intelligence. So first of all, there are easy limits to see and to understand. First of all, those systems, if you read closely how they work, they require really a lot of interaction with the game or with the world living to learn how to play. So for example, AlphaGo, to learn how to beat the best human player in the world, needs to play either against itself or human players. It needs to play literally thousands of millions of games, which is more than the number of games that all the human players on Earth have played in all times. So that this is very slow learning. Another thing is that those systems, they are made to learn a single task, a single predefined task, in that case, the game of Go. And I will explain you in a few minutes that there are fundamental limitations behind the system that make that, for example, you take AlphaGo and you put him in front of a 5-year-old child for playing the game of checkers. Checkers is a trivial game. It's really very easy. It will not even be able to understand the rules of the game. So not only it will not be able to beat the 5-year-old child at the game of checkers, but it needs an engineer to open the brain and to retune a number of things. And okay, by the way, also those systems, they are deeply unstable. Like what you see in the news is basically the systems that are the best out of the many simulations, the many training regimes that were performed on very high performing computers. But what you don't see is what the percentage of times it failed. To go into a little bit more detail to understand some of the limitations of the system, I will just outline very grossly what it looks like inside the brain and in the environment of those systems. So let's take, for example, the AlphaGo system or those systems who play video games. And basically, we can see two parts on this diagram. There is a blue part, which is basically the software, the algorithms that are implemented inside the artificial brain of the machine. And this artificial brain is interacting with the outside world, which is in simulation, in that case, a video game. And it's basically interacting with that external environment by performing actions. And then it is getting back from the environment two kinds of things. One kind of things is a perception of the world state. And another kind of thing is what we call a reward, which is basically, for example, in the case of video games, the current score, the number of points that the agent has accumulated so far. And then inside the brain, there are a number of machinery who try to detect regularities in the flow of actions and the reward and the perception that they trigger. And they try to optimize the sequence of actions that are needed to maximize this reward that is given out of the environment. And the thing that is very important to see here is that this reward is not inside the brain of the system, it's really outside. It's really like a specific wire that the engineer has taken from the system and has put in a specific part of the software and told the system, this is what you need to maximize, okay? And so it means that, for example, if you want the systems to learn another video game, you can't just put the system in front of the screen of the video game. You need an engineer to really take the wire, okay, reprogram, and say, now this is this number who comes from this program, which is actually a relatively completed program here made by the game designers to compute the score. It's actually a non-trivial program. And so the engineer has to tell, it's now this number that you have to maximize. And so this is one of the reasons that, indeed, every time you have a new task, even if it's very similar, like another video game, the system needs the engineer to intervene. And actually, in games like AlphaGo, the engineer does much more work. For example, the engineer is also pre-specifying what are the moves that are possible in that game. And it's a kind of pre-formatting the representation. AlphaGo does not work from the pixels, for example. So when you look at that, you quickly discover that it's way, way, way different from the way human children are learning. So first of all, if you look at the way human children are learning, there is a big difference, which is they don't learn a single task, a single thing, but during all their life, they learn an open repertoire of skills, which is ranging from learning how to look around with their eyes, to follow moving targets, to sitting, to locomoting, to grasping objects, to doing bicycles, to play the piano, to speak, all range of things. And the thing is that, as you may have noticed, I hope so, no engineers open the brain of a child for any new task he has to learn. It seems quite obvious, but it is actually the state of most machine learning research. For every new task, you need to open the brain. That's it. Another thing is that the tasks that children are learning basically lie in much higher dimensional spaces. So what does it mean? Not only they see the world through their eyes, but the way they interact with the world is with a body with hundreds of muscles that they control in real time through approximately continuous motor commands. And so typically every millisecond, there are hundreds of muscles who are put into actions. And these are continuous actions. For example, in video games, like in the Atari games that are used by Google DeepMind, the action is like a discrete, like a choice between like pressing the button, go up, go down, go left, or go right. Okay, so that's way more simple. And the thing is that those children, they learn those skills not by doing billions of interactions with the environment, but much less because the only way they can collect data is by moving in the physical world. They do not have access to a simulator of the world, which they can run for hundreds of billions of times in big computer clusters. They live in the real world, and the only way they can learn, because they don't have a database of training example that is provided to them by an engineer, again, is by physically moving in the world. And so if you compare the size of the sensory motor spaces in which they live, the diversity and the complexity of the skills that they learn, it's really like orders, like light years from what, for example, deep reinforcement learning research is able to do so far. But so what is happening? What are the mechanisms that drive infant development? So that's basically the object of study of a domain, which has been called for a number of years developmental robotics. And this is actually the domain in which my team is working, which is organized along several dimensions. The first dimension is, okay, basically, we want to understand intelligence. We have an extraordinary example of intelligence in the world, which are animals, and in particular, human animals. And we want to try to understand those principles first as a way to really understand how they can solve those problems. And so basically what we do is that we team up with cognitive scientists, and we build computational models of the way they learn. I will give you some examples later on. And then, obviously, as we are doing that, this gives us ideas about how to explore new algorithmic principles to build machines that are able to learn a bit more autonomously. And then, I hope I will have time to say you a few words about that. We can actually apply both new understanding of the way humans learn and develop their cognitive and sensory skills, and use also new insights in machine learning to apply those techniques in the domain of education. How can this help us, children and also adults, to learn better? Okay, so there are many mechanisms that are at play during infant development. We cannot study all of them at the same time. One of the problems that we study in my team is the general problem of exploration, which is related to what I just mentioned to you. One of the big major problems that the child has is that the only way to learn is by collecting examples in the physical world, and because it takes time to do experiments with his body in the physical world, it can collect only relatively few examples. So basically, if he explores randomly, like he makes random movements in the world, he will not explore very efficiently, collect data which are little informative. And so how can it actually organize its exploration? What are the mechanisms that guide its exploration? And there are several families of mechanisms that are known in developmental psychology and neuroscience. Well, when I say known, we know it seems to be important, but we don't know really how it works. And so what we do is we try to build computational models, algorithmic models of them. And so there is one family which I will talk to you a lot about today, which is what we call in everyday language curiosity. Another family, which is what we call cognitive biases. Cognitive biases is basically the kind of prior knowledge you can put in a system to boost inference. So for example, if you think about learning language, human children learn the meaning of new words extremely quickly. Like when they see, for example, a chair, you don't need to tell them 1 million times the word chair associated with 1 million images. They got that very quickly. And so they are probably doing something a bit different than mere statistical processing of raw pixel images. And one of the biases that they are using is, for example, in that case, to try to guess the meaning of new words in terms of what is the actions they can do meaningfully with the objects or with the image that they see. And when they see a chair, typically, they are not going to try to guess the meaning of that in terms of the color of the thing, or in terms of, I don't know, the height of the thing, but rather like how their body can act with that thing. And in general, they've already played a lot with chairs, and they have seated on many things. And they will basically guess that chair is something on which you can sit. So that's an example of a cognitive bias. Another family of biases that we are studying is the role of body, the role of embodiment. The fact that learning does not happen in a brain in a vacuum, but it happens in a body which has physical properties, which can, for example, facilitate the acquisition of sensory motor skills. So one example, for example, is learning how to grasp. Grasping with a robot is known to be extremely difficult. But as you may have noticed, most robotic hands, for example, they are made with metal. And metal is a very slippery material. And so grasping an object, for example, with a gripper like this, you know, it's a bit like there are games in, so it's extremely difficult. And the way we humans manage to grasp object is not by making complicated calculations about the trajectory of our hand relative to the geometry of objects. What we are leveraging the fact that our hands are soft. It's basically soft. And so basically most of the objects that are around, basically we need to put, I don't need to actually even look at the object behind me. I just touch it, I close my hand, and that's it. Okay? And I didn't do any calculation, and it doesn't fall down. And it's a lot of this is done not by algorithmic computation, but what's called morphological computation, which is my hand is like a bunch of soft fingers with some kind of elastic reflexes. And it's a bit like water. When you fill it into a bottle, it takes automatically the shape of the bottle. Have you already realized that? And it does not compute the shape of the bottle. It does not even have sensors to perceive the shape of the bottle. And that's the way we grasp objects. That's the role of the body. And then another family of learning mechanisms is social interaction. So let's go to curiosity, to intrinsic motivation. So more than words, I will show you a video. Here we see a video of a child that is in the home of his parents, probably. I don't know, we don't see the parents. But by the way, it's very important that we don't see the parents. The parents are not there. And he's anyway doing things. He's exploring the world. It doesn't seem that here he's kind of trying to solve a problem that the parents gave him. And if he solves it, he gets like a bonus. And if he does not solve it, he gets a punishment, like in the reinforcement learning scenario. If he was a bit rational, for example, if he would want to maximize its chances to grow old, then to reproduce, to get rich, to have social recognition, then probably at this point, the safest way to grow old would be when his parents are not there, to just stay on his bottom, do nothing, and try to avoid putting his fingers in the plug, for example. That's very dangerous. But this guy doesn't sit on his bottom. He's exploring everything he does. He's opening things, maybe he's breaking things, and sometimes actually he puts his fingers in the plug. But he learns many things during this exploration. And it seems that this kind of learning seems to be really fundamental in the way humans learn, spontaneously learn about the world. And it's actually related to what psychologists have been calling intrinsic motivation. So from the 50s of the last century, there are a number of psychologists like Berline who have basically generated the hypothesis that maybe in the brain there are circuits who are rewarding organisms not only for finding food, not only for protecting their body, not only for reproducing, but also for the mere pleasure of learning. And so, for example, people have talked about things like the brain might be interested by experiencing novelty, surprise, cognitive dissonance, challenge, or whatever. But the difficulty is that this literature on psychology has remained relatively vague, like it's words, it's psychology. So we've been working with a number of labs in the world in the last decade to try to develop algorithmic models of what could be happening here. And as I was saying, it's basically a very interdisciplinary kind of research. It's basically research that's done where you have AI, robotics, machine learning lab, but you have also cognitive neuroscience lab, developmental psychology labs. And so what is the conceptual perspective that we take to approach this question, to approach the question of what are the mechanisms that are driving such kind of spontaneous exploration we see in organisms? And so the perspective is the following one. We basically make the hypothesis that the child is a kind of sense-making organism, in the sense that it's fundamentally internally driven to make good predictive models of the world, and even more importantly, to build predictive models that enable to control the world, to discover what is controllable and to learn how to control it. And the way to do that is by exploring. And when they explore, there are several kinds of strategies. Strategies are basically the kind of questions that they ask to the environment. So for example, one kind of strategy is asking a question like, okay, guys, we are right now like this. What happens, for example, if I add this piece of wood here, or if I remove this piece of wood here? So they do the experiment like little scientists, and then they observe. Another kind of experiment they can do is goal-oriented, in the sense that, okay, for example, these little children, they are mixing chemicals, and they are trying to see what they can do with it. And at some point they say, okay, maybe could we make a mixture which makes all those liquids transparent? So they imagine this goal. Let's put the liquid transparent. And then they try to use their current knowledge, which initially is very, very poor, about those chemicals, and they attempt to make a transparent liquid. They don't manage. But maybe they discover as a side effect how to make a black liquid. And by doing that, by setting a goal, which is maybe actually not even possible to reach, or maybe sometimes it's possible, but they do not know how to do that, most of the time they will learn as a side effect how to solve another problem. And this other problem and the solution they just discovered is going to get back into their tools about how to solve and to control the world, and it will progressively accumulate as they grow up. And so now we can imagine new kinds of algorithmic architecture. And if I take the same kind of drawing that the one I showed you at the beginning that was illustrating the principle of deep reinforcement learning, here is a modified one, and there are a few important differences. One very big difference is, first of all, here you don't see anymore a box which is in the environment and which is computing what's called a reward, so a real number, a score if you want, and which is plugged inside the brain of the agent and with a related objective of maximizing that score. This has completely disappeared. But then inside the brain, you have a few more boxes. There is still one box which was already present in the first figure, which is learning predictive models of the world, which is basically learning to predict the regularities. For example, like when you do certain sequences of actions, what kind of sequences of images or sounds will you observe? But then there are also new boxes. One is called sample goal. And sample goal is basically an internal algorithm that is going to imagine some goals in the world that the internal model shall try to achieve given its current knowledge of the world. So what could be a goal? A goal is typically a certain regularity of the flow of actions and perceptions. So a goal could be, for example, I would like to see an image with a big green blob in the center, or I would see an alternation of blue and green, or I would like to hear a big sound with this kind of fundamental frequency. So the system can imagine those goals, and initially actually it has no idea which one are possible, which one are impossible. And so it will try those goals and progressively improve its internal predictive model. And there is this other box, and this other box is quite crucial because this other box is going to help these mechanisms to decide which goal to sample. Initially, it will probably do things randomly, but probably progressively it will sample goals that are a bit more interesting. But then the question is how exactly this internal goal generation and selection can happen. For example, what is an interesting goal to sample in the world? There are many hypotheses that have been considered in this community. For example, you could consider that an interesting goal is a goal which leads the brain to experience novel states or states with high entropy, for example. You could imagine that an interesting goal is one which makes the brain experience surprise. So surprise is a bit different than novelty. It's kind of, you are making a prediction, you are sure of your prediction, and then you observe something very different from your prediction. Another measure comes from physics, and it's called free energy, which is actually related to the minimization of surprise. And so, how do you select among those potential different measures? So, one way to select is actually to put machines and to imagine them in the same kind of environment as the babies, like a physical body, a rich set of sensors, not a lot of prior knowledge, and you see what kind of exploration mechanisms, what kind of dynamics it leads to. And so, for example, if you put a system with an intrinsic motivation to maximize states or situations where it's making a lot of prediction errors, it will do very strange things. So, for example, your robot may happen to spend it all day making strange gestures, looking through the window of your office. And when you open the brain to try to identify what's happening, you discover that it's trying to predict and to control the color of the cars or of the shirts of the people that come through the window, depending on the movements they make. Why shouldn't it be possible? It doesn't know. Babies don't know that their bodies don't control the color of the cars passing the window. But they learn very, very soon that it's not very interesting and it's not controllable. And so they do more interesting things. So what are those more interesting things? So for example, one very useful and efficient heuristic that has been studied for a number of years is what we call the learning progress hypothesis. So basically, the learning progress hypothesis is basically a mechanisms where, when you imagine, for example, you have 4 activities, 4 kinds of goals you can imagine. And imagine that, for example, you have one goal that is at the beginning you control and you predict very well. So here is time you practice that goal or that activity, and errors in the control or errors in prediction are very low, and it stays very low. And then you have 3 other activities or 3 other goals which are initially very difficult. One stays very difficult, but the other one gets easier and easier with different rates. And so the idea is that it's quite efficient to learn a good world model to first focus on the goals and activities that maximize learning progress, which is basically the derivative of those curves, which is basically exploring priority those goals where the model, the predictions of the world improves maximally. And at the same time, avoiding those where you make no progress. So either those that are too easy, and so there is no progress, or those that are too difficult. And so when you do that, you will, for example, in that abstract case, first explore activity number 3. And at some point, as you learn, it becomes less interesting because there is less progress. And you shift automatically to the more difficult activity while avoiding the one that are either too easy or too difficult. So now, how can this be made to work in practice? So I won't bother you with details of algorithm, but just to give you a rough idea of how it can be made to work. So imagine a robot which is perceiving the world through its cameras, okay? And first, there is some kind of unsupervised learning mechanism, which, given the images, try to learn a compressed, low-dimensional representation of those complicated images. And so this can be done for those who know with a family of neural networks, which are called variational autoencoders. And this gives you a low-dimensional representation of the things, if you want, that can move around in that world. But then among those things, there might be things that are controllable, other things that are not, some that are easy to learn, some other that are difficult to learn. And so this space, we call that a latent space, we can use that space to imagine goals in that space. Like, for example, we could select a few of those dimensions, which might correspond, for example, to the position of one of the underlying objects of that world. And the system can imagine a goal, like, for example, I would like these 2 latent variables, which correspond to one object, to move in that direction, for example. And then it's using its internal model, it's trying an action that it thinks will achieve that goal. In general, it won't do exactly that, but it will enable to collect new data and it will update the internal model. So let's see that in action in an experiment. So here we have an experiment where we have a robot who knows initially nothing about the world. And it can move its motors here in the arm. It does not even know the shape of its body. And then here, let's assume there is already a phase of unsupervised learning with a camera, and that now is able to relatively well identify and track the movements of multiple objects in the environment. In the environment, there are objects that we know as humans he can control. So for example, there is his hand, there are these little things in front of him, and actually one of those joysticks is controlling this electric toy that is here. And this toy can actually push that ball, and that ball can actually, when it's pushed on the side, produce some light. But there are also many other objects, like objects who don't move, but that are too far away to be controlled. And we also add a number of free moving objects in the environment, which cannot be controlled at all, but the robot doesn't know. And so if we get this system to explore and learn for a few hours, typically we will observe a progressive organization of its behavior and a progressive acquisition of skills and discovery of what can be controlled, what are the possible outcomes, and how to control them in that way. And so first of all, it will discover this robot. Initially, it will try to imagine some goals about all of the objects in the environment. For example, he might take this white thing and you might try to push it on the right or on the left. And initially, you will not manage to do anything because it's too complicated at this stage of development. You might also pick up this object and try to move it right or left or in another direction. But then very quickly, it will discover that among all the objects, there is one of special interest in terms of learning progress, and that is his hand. And so it will focus exploration on selecting goals for moving the hand. And by doing that, it will actually improve the diversity of movements he is doing with the hand, and this will increase the probability to discover as a side effect how to move those two little things. And so then, as he discovers how to move those two little things, he gets interested and focuses on trying to move them in even more diverse manners. And quickly discovers that one of them, actually the other one, is moving also the little white object in front of him, the electric toy. And so now the electric toy is the source of learning progress. And so he generates goals on it, and very quickly he discovers that it can move the ball around. And so basically what we observe is that in a few hours, this typically takes 5 or 6 hours, and it's not using a computer cluster that is costing in energy, I would say a certain percentage of the nuclear plant. It's using a Raspberry Pi. In the real world. And so in a few hours, it discovers basically how to move that ball. And actually, even in quite original manner. This, we didn't expect it could do that. And we never told this machine that, for example, there is an objective, like I want to move the ball forward, that the engineer is interested in. And not only we didn't give him this objective, but we actually complicated his world by putting some distractors that can't be controlled, but still he has to discover that through the thing. What would have happened if you would have used a system like AlphaGo, and you would have pre-programmed a reward function, which would be 1, for example, if a score of 1 if the ball moves of 1 centimeter forward, 10 if it's 10 centimeters, 20 if it's 20 centimeters, 0 if it doesn't move. And then you use AlphaGo. Well, AlphaGo doesn't work at all. You can wait 1 million years. It does not work. And why it doesn't work? AlphaGo is extremely smart to optimize a policy once it has found a few ways to get rewards. Once it has a little bit of information about how to produce rewards, like once it found a few ways to move the ball, then it becomes very smart. But before that, what does it do? Just random exploration. Random exploration of actions in this arm will do that. Something very shaky like this, and you can wait very long before it discovers all this chain of action. So by changing completely the perspective, I don't even give the objective to the robot. It's free to select its own objective, its own goals. It's going to generate a self-organized developmental trajectory and then make those discoveries like how to move the ball and a number of other things. Then this kind of experiment you can do in many other setups. And you can actually extend the idea, extend the principle. Here is a setup where a robot is using the same principle, but not only is able to imagine goals by himself, for example, putting this red thing around, so he's learning how to fish. I hope you appreciate it's very important. But then, as you can see here, he can get help from a human, and the human, for example, can physically take the body and show him a movement. And maybe actually there are several humans from which it can get help. And actually in that case, it's not the human who decides to give help. It's the robot who knows he can get help, who knows he can ask help from several humans, and who will actively decide when he asks help, what kind of help he asks, and what he does with the information he is being shown. For example, if he sees a demonstration of what a human is doing, maybe he could try to emulate the same goal, like to try to reproduce with its own repertoire of actions to do the same kind of end effect, or maybe he could mimic the movement. And maybe by choosing one or the other way to exploit the information, he will learn different things. And all of these things is choosing with the same kind of heuristics, which is estimated the empirical learning progress to be gained out of that. Okay, so just a little comment to come back to the video games. There were a few video games like Montezuma Revenge, which were actually very difficult to solve with AlphaGo-like systems. And quite recently, actually, people, especially at Google DeepMind, by the way, reused the kind of idea I just presented to update the deep reinforcement learning systems and to get them when they don't get any information about the task the engineers want them to solve. Instead of doing random exploration, they get curious about the environment in the same similar way I just presented. And it enables to solve some games which were completely insolvable without this kind of idea. I will just conclude by one quick mention of the kind of application this can lead to, because to just up to now, what I described to you was really quite fundamental work, fundamental theory about the nature of autonomous learning. But actually, if you look at the kind of model, the kind of heuristics I presented to you in the robot experiment, what was it about? It was about like you had a lower level system which was trying to detect regularities in the flow of actions and perceptions, and a higher level system which we call meta-learning system, which was trying to generate goals, a sort of curriculum learning of goals to maximize the efficiency of learning of the lower level system. And it didn't make any specific hypothesis about the lower learning system. So what you can imagine is, okay, maybe we can use this kind of autonomous curriculum learning system for driving the learning, not of an artificial neural network, but of a real neural network, of a very deep neural network, if you want, which is that of human brains. And so this is exactly what we've been trying by designing educational applications. And basically here it's about learning mathematics concepts, like decomposition of integers and real numbers. And basically we use exactly the same algorithms, but to sequence the order of exercises that are proposed to children. And we've done large-scale experiments in primary schools in Aquitaine over several hundred children. And what we could show is that if we compare this kind of system with a system of personalization which is handmade by a specialist in the didactics of the science of mathematics, then we still can do even better with this kind of automated system, not only in terms of learning efficiency, but also in terms of motivation. And that's not completely chance, because as you remind, this mechanism for efficient learning comes initially from modeling the mechanism of intrinsic motivation in children. Thank you.
Merci Pierre. Pierre-Yves. Des questions pour Pierre-Yves? La première est toujours la plus compliquée. Là.
Là.
You mentioned that when you explore the space at random until you have some reward, you don't know where you're going. And so, of course, the answer to that is having some differentiable objective function. So how is this differentiality would interact with your system?
So one way to see the kind of system I presented, I also is like the kind of goals that the system generates to themselves, as they are decided by themselves and not by someone externally. They can decide actually to generate differentiable rewards or differentiable goals. So, for example, which can be much easier to learn than an external reward. For example, the score of video game, which can be very sparse in the sense that maybe it's only one when you have done a sequence of complicated actions, and it's zero everywhere. When you decide what are your own objectives, you can actually decide their properties, and you can decide in what orders you select those properties. And this is one of the things which also is a strength of this kind of thing, is that it enables the systems to first focus on the easily learnable parts of the environment, and then could go to the more complex ones.
OK. D'autres questions?
Just from the mathematical point of view, are you using filtering for the predictions, for example?
Filtering techniques can be used in several parts of such an architecture. It can be used quite traditionally for learning a forward model, for example, for learning how to predict the consequences of actions. But it can also be used, for example, for estimating what we call the learning progress. And here, actually, we have kind of a challenge, because ideally we want to have a good estimate of what kind of activities and what kind of context produce high learning progress, but we don't want to spend too much computational energy and to sample too much part of the environment to have a good estimate. So what we do is we are using heuristic filters to do that, and we basically favor speed against accuracy in practice.
Sorry, and so which kind of filters do you use? What is the name of these filters?
Well, the kind of filters we use here are very, very simple filters, like running average, differences of running average of the error in local parts of the environment. So typically, the way we do that is that we split the environment in hypercubes in ways that are finer and finer, and at various level of what was the English name? at various levels of granularity, we do this evaluation like we do have a running average at different time scales, and we compute the differences on that. So that's very simple filtering, but it has the advantage of being relatively fast and computationally cheap.
I'm a frustrated parent. I'd like some insight from your model. Why are children so horribly repetitive?
So first of all, repetitiveness can be in the eye of the beholder. Like there are regularities in the world that seem very obvious to us, but that are not obvious to children initially. And like, for example, if we see them repeat the same kind of gesture many times, first of all, it's not necessarily always exactly the same. It's a small variation. And the second thing is that it might take them some time to identify the regularities in there. So this is the response of your question from this perspective. But then actually, another thing I didn't discuss here is that children are equipped not with one single source of internal motivation. There are many competing ones. And actually, they have also strong homeostatic motivations. Not only homeostatic motivation in terms of keeping safe and finding food to keep their physiological variables, but also actually homeostatic cognitive variables. And it seems that I have some colleagues, and we have also worked on completely opposite models for learning, which are basically trying to always find yourself in predictable situations, and basically conceptualizing learning as reacting to external perturbation to come back to very predictable patterns of interaction. And it seems it's possible that there are these two kinds of forces that are happening into the motivational system of the child, but we don't really know how they are arbitrated, to what extent they depend on the mood or on the personality. This is completely open questions. But clearly, there are ideas of homeostatic cognition, which then make repetitive action completely natural. But we have to say, all these things about understanding how the motivational systems work in humans is mostly unknown territory.
Oui.
First of all, thank you very much. I've been following this work since Barcelona in 2016, and I agree with you that I think it's far more interesting than what we're kind of doing on the RL side. What I'm very curious about is if I think, I don't know how a baby thinks, but as an adult, when we're exploring state space in like the real world, like a robot is doing in your experiment, often before we explore state space, we have some preconceived notions of the environment and how we interact with it, and we actually run simulations internally. And I'm very curious to understand both, how do you believe actually younger children do this? Are they running simulations before they're interacting? And second, have you considered actually, or right now you're just using the variational autoencoder and interacting with the environment to actually have pre-trained models that are essentially simulators to combine with the actual robotic actions?
Yeah, so you're right on the 2 points. So first of all, in all the models that we use, there are always internal simulations. This is what we call the internal model, which can be very simple, but it is a form of learned simulator of the world. And when in any of those models, the system imagines a goal to decide for the action sequence it's going to make, he is making an internal optimization scheme using the internal simulator to try to guess it. So that's the first thing. The second thing is that indeed, by the way, as he explores the world, the internal simulator improves, and it means that when he encounters a situation, later on, it might become learnable because now he has some priors in its simulator that he has learned before. And of course, there is the question of maybe you can even have, if you want to take a more engineering perspective, for example, you can even use available simulators of robots and use them to actually transfer to the world. We actually do that in some of the experiments. And last of all, there are also like kind of not learned, but like innate biases. Like, for example, something I did not detail in this robot is that, for example, the motor primitives, the way he makes movement, is not by unstructured neural networks. It's using things which are called dynamic motion primitives, which are kinds of dynamical systems, which model things like neural synergies in the human body. Like in the human bodies, when the babies, for example, they come to the world, even when they are in the womb of their mother, they don't do random movement in terms of random action every millisecond. They send high-level commands to relatively complex neural systems, which then produce a dynamical system which has already some structure. And this helps to carve so it's related to embodiment.
Did I answer your question? No, non plus.
Hi, I like to talk very much, and there's one point that really caught my mind, which is about the baby predicting the color of the car by shaking its hand. So it made me think about what the algorithm is doing, and you're focusing the reward function on curiosity. And I would like to understand if there is a way of focusing or creating a reward function that focuses on causality, because just saying that you're curious is not sufficient.
Yeah, okay. So there are several questions in your question. The first thing is that, okay, as I said initially, the word curiosity is more an everyday word we use to speak about various kinds of spontaneous exploration in humans. But we don't know what it is from a scientific point of view. Okay, so this is why, for example, in the collaboration we have with neuroscientists and psychologists, we build algorithmic models of spontaneous exploration, and we discover that there are many different forms of mechanisms that can lead to several forms of spontaneous exploration. And then this lays the ground for a scientifically informed discussion whether we can decide what we would like to call curiosity or not. So that's the first thing. The second thing is that among the many different ways to implement curiosity, some of them are not related to the action system. For example, you can imagine a system which is motivated to find new places in the world where it's going to be able to see like stimuli move in with a particular pattern with high entropy, low entropy, medium entropy. This is independent of their action. It's like they want to see something, do something. But then there are other kinds of systems, such as the one I presented to you, where actually the incentive is basically to learn, to discover parts of the world that it can learn to control. Which means where it can learn a causal relationship between its actions and the environment. So basically, the robot learns by making physical interventions in the environment and trying either to predict the consequence of those physical interventions or to reach and imagine goals with those physical interventions. So in a way, indeed, this system is motivated to find aspects of the causal structure of the world.
Did I answer your question, Ravi? Question? Oui, il y en a une ici.
Thank you very much for a very interesting presentation, and especially the results, very impressive. I'd like to know if the robot can learn and reuse the models that it has learned.
Yes, actually, recently we did an experiment. Okay, you know, in this deep reinforcement learning literature, there are a lot of benchmarks. Benchmarks like at Oregon, but also benchmarks with simulated simple robots. And some of those benchmarks, the goal is, for example, to get the robot learn to walk or to run as fast as possible. And what we did as an experiment is first have those simulated robots be subject to unsupervised learning with this kind of system, like system driven by curiosity. It is not given any reward function, okay? And then the learned model, the learned part of the world, that is the result of this system, is given as a starting point for a classical deep reinforcement learning system, which is only trying to maximize the extrinsic reward. And so by doing this, we are able to show that it's enabled to solve the problem much faster. So that's an example where you can imagine how the kind of model that you learn can be reused later on. And more generally, it is especially useful for a family of reinforcement learning algorithms, which are called model-based reinforcement learning algorithms, which are basically algorithms which are separating the learning of the dynamics of the world, which is basically learning when you are in a given state and you do a given action, what is the next state, from learning the mapping from states to reward and how to find a sequence of actions that maximize this reward, which is then specific to a particular task. So you can basically reuse the model you've learned by one approach for solving a task which you don't even know exists at the when you begin to learn.
Right.
Thank you very much for this fascinating lecture. I just have a point of curiosity, actually. I'm sure you're familiar with the recent work also of Judea Pearl, who famously in his book of Why introduced, not only made the provocative claim that deep neural networks are essentially gigantic correlation machines and learn nothing but associations, but he also introduced this ladder of causation, where beyond association there is intervention, which we clearly see in your models, and also counterfactuals, hypothetical thinking, which may be present given what you told us about simulations. But an interesting point about counterfactuals is that they are causal in the sense that we can reason about what would have happened if, or if some condition would have held that in fact did not turn out. So I would be curious how deep you already entered into this realm of counterfactuals with your models.
Yeah, so there is some form of counterfactual learning which is happening and which is actually fundamental to those systems, which is, okay, when the system is imagining a goal, let's say, for example, he's imagining the goal of moving an object in front of him on the right, okay? And then he uses his internal model to try to guess what's the optimal sequence of action. And let's say, for example, he does this. So I actually moved it a bit on the left, for those who didn't see. He didn't manage to solve at all the goal he imagined. But then he still observed an outcome in the world. And then every time he does that in the system, then after the rollout, the experiment, it has then a phase where it is imagining, okay, but then if I had imagined going to the left or going to a bit in this direction or to this direction, then this information would have helped me to improve toward those goals. And so there is some kind of internal replay of the data by imagining other goals than the one which are currently at play during the rollout. And this is actually a very fundamental aspect of the efficiency of those algorithms.
Une autre question ici?
Thank you very much for your great presentation. I was wondering about if you were thinking of associating in your experiment several robots, for example, because children might be able to learn better if there are several of them in a room, or if they are interacting with each other. So I was wondering if you have any
thing about but that's a very good question. So let me take this opportunity to show a funny experiment, which was not a scientific experiment, but an artistic experiment we did a few years ago. And actually, it was at Fondation Cartier pour l'Art Contemporain. And here we have not one, but 5 robots. And they're equipped with a similar curiosity-driven learning mechanisms as the one that was used before. But then they are also equipped with algorithms enabling them to learn by imitations, movements made by each other, or movements made by humans visitors. And they are also equipped with mechanisms to learn and to invent their own language. So they play language games. They try to invent names and to negotiate which name they will use for naming this movement or this color or this object. And there is actually an interaction going up through those different processes, because, for example, through curiosity, they might learn new movements, ways to push objects. Those objects were designed by the movie maker David Lynch. Don't ask me what they are supposed to represent or whatever. And when they explore by curiosity their movements, they discover new movements, and those movements can then become imitated by the other robots. And those movements, when they are imitated by those robots, they can then be reused in their curiosity-driven exploration. And then they can also become the object of language games, like they can become the object of names they invent to speak about what they discover. So here there is truly a dynamics where the cultural dynamics which is interacting with the local curiosity-driven learning. It is only one very small aspect of what you can expect behind your question, because there are many, many other interesting dimensions. But it's just to say, yes, that's a very cool question, and there are many things to do here.
L'aspect du robot, c'est Eraserhead, le premier David Lynch.
Yes.
Une autre question? Another question for Pierre-Yves? Question? On the right. Ici. Oh, over there. You have it.
Thank you for a great talk. So I have a question that's maybe more a personal question. And feel free to say it's not for you. But did you give any thoughts about the ethical aspects of all this? And either on building autonomous robots or on uncovering things on the human mind, how it works, how this could be misused.
Okay, so actually, I'm spending a relatively important part of my time on ethical issues of AI. And I think actually one of the most pressing ethical issues of AI that we have today are not about potentially autonomous robots that may take over the world in the future, but they are about existing machine learning systems which are orienting the attention, the information that everyone gets on the everyday use of the big systems. And I try to spend some of my time explaining those problems of the current systems, and maybe also it's useful to realize that, interestingly, these are the companies who are building those large-scale recommendation systems, which can have very good positive effects, but we are also very dangerous, who are currently building ethical boards and attracting the attention of the media and of the larger people on the risks of potentially autonomous systems that might take over the world. This is probably the best strategy if you want to draw away the attention of the public towards the real problem of today. So this is one part of the answer. Another part of the answer is that, okay, all the things, I am not claiming at all that any of those things are anywhere close to the kind of intelligence and complexity of real humans. Actually, what the basic activity of our research is to build algorithmic models to help us understand better human intelligence. I didn't speak a lot about that today because it's a machine learning meetup. It's not a cognitive science meetup, but probably half of my activity is about cognitive sciences. And basically, when we build models in the sense that those models of, if you want, curiosity of learning, it doesn't mean at all they work. They are systems which are like substantially similar than human learning systems. In the same way that, for example, when you build a computational model of climate, it might be extremely useful to understand and to predict the climate, but there is not a real storm in the climate simulator. There is only a model of some of those principles. And those principles, the way we model them today, they are really very, very simple, you see? Very, very simple. So I think you're right to say ethical things are very important. I think we have to look at the ones that are really important today, and then we need to think about the kind of applications that you can use that are more societally useful. So, and that's why, for example, in my lab, we chose to develop the educational applications, because we believe that indeed there are potential misuses of machine learning techniques, but we also believe there are potential very good and useful uses.
Okay. Another question for Pierre-Yves? Or are we,
I have one question. Is there any way to imagine the robot you were showing that was running on Raspberry Pi, like having it at home, for example, and trying to learn from community usage and have it doing a lot of stuff? And, yeah.
Okay.
Would it be possible?
It does happen that the robot you've seen in the experiment, so let me just show it again. It does happen that
it does bad things.
This robot, we made it in my team, and it's completely open source. It's called Poppy. Actually, there is a family of robots. There is Poppy Torso. This is Poppy Ergo. We have a full humanoid robot. Everything is on GitHub. There are companies selling pre-assembled things. And actually, there was recently an association that was built with a number of large educational French institutions, was just created 2 months ago to disseminate those tools, actually not primarily for researchers, but to a much larger community, which is education. So actually this robot, the little one here, is right now used in several dozens high schools in French as a tool for learning computer science. So yes, it's all accessible. It's a bit costly because you need to print, you need to buy the motors, but it's accessible.
Okay. Another question for Pierre-Yves ou pas? Ok. Donc on remercie Pierre-Yves. Donc Denis va être le prochain. Alors ce qui est assez drôle en fait avec Denis, c'est qu'il a travaillé en fait avec Gaël Varocco. Gaël, on l'a eu, je crois, au 4e ou au 5e meet-up au tout début de la première saison. Et quand il finit son talk, on se pose la question à un moment de c'est quoi la mort? Et c'est comment est-ce qu'on reconnaît quelqu'un qui commence là, végétatif? Et donc on se pose beaucoup de questions. Et en fait, toutes ces questions-là, c'est pas des questions stupides du tout. On s'aperçoit en parlant un peu avec Gaël et on parle un peu avec Denis et on s'aperçoit qu'il y a en fait beaucoup plus de choses là-dessus. Donc Denis, tu vas... Alors, ça marche ou pas?
Ça fait un joli scratch.
Ouais, ça fait un scratch.
Continue, on va faire du rap. C'est pas grave, vous intervertissez?
Ouais, mais t'as pas envie de prendre le micro, sinon il y en aura un autre.
Un, deux.
Ouais, tu veux essayer celui-là? On l'arrête, celui-là. T'en fais pas. Il est parti.
Le micro sur la table.
Ah, mais en fait, c'est autre chose.
Non, il est pas branché. Un, deux.
On commence à avoir un petit Arsène. Éteins
Attends. Éteins le micro-cravate. On a besoin que d'un seul micro pour le moment. Il est éteint. Attends. À l'intérieur. Donne.
Il est éteint. Ah oui, t'as raison. Ouais, c'est celui-là qu'on éteint. Tu ouvres. Voilà. Il faut laisser de
Ok, c'est mieux.
Ouais, ça a l'air d'être
Ok, c'est l'interaction entre les deux.
Donc, allô? Ouais. Vas-y, tu y vas?
Attends.
Mais il y a un autre problème. Ouais. C'est ça quand je parle? Ouais. C'est bon comme truc.
Clignote, mais. Où est l'autre? Est-ce que l'autre est éteint? Il est dans l'autre. C'est le bon. Parce que je le vois pas. Alors, le Finder. Ici.
Je le fais.
Donc, merci à Denis de venir et de nous parler de conscience. Vas-y, le trouble de la conscience. Voilà.
You got my slides?
Hein, ouais. Et donc, tu essaies de parler devant tes slides? Voilà. Ok, super. Merci.
Tu peux dire qui tu es en attendant?
Yeah.
Vas-y.
Igor, thank you very much for the invitation and the kind introduction.
Okay.
Before I get started with my presentation, maybe you're curious about learning a little bit about my background. So I have a background in psychology, actually. I'm a certified psychologist. I obtained my diploma at the University of Gießen in Germany. And I obtained also my PhD in psychology at the University of Cologne. And during my PhD, I actually specialized in electrophysiology and started to develop open source software for analyzing electroencephalogram and magnetoencephalography data. And started to get more interested in machine learning. And my work brought me to Paris. Today, I'm a researcher at the INRIA-Saclay Institute. And what I want to share with you is my work that I conducted in the last 4 years. Actually, in the context of my, I started this work in the context of my first postdoc project. And I finished this work today, a couple of weeks ago, so to say. And this is going to be about random forest methods for EEG-based diagnostics of disorders of consciousness. First of all, here's a little bit of a practical motivation. So disorders of consciousness are really important in the intensive care unit in neurology, and they are quite tragic. So as a result of accidents or cardiac arrest or strokes, people can end up in a very troubled situation in which they do not have any longer a consciousness or awareness as we know it, that does not allow them to communicate with us. Prominent categories of disorders of consciousness are the so-called unresponsive wakefulness syndrome, or also historically called vegetative state, and the minimally conscious state. And the phenomenology is quite complex in these two diagnostic categories, but both have in common that people are more or less aware of what is happening to them and what is happening around them. And what makes these disorders of consciousness tragic is that the primary reason for death in disorders of consciousness is actually the decision to end a life-supporting treatment. And the problem is that the diagnosis of disorders of consciousness, despite all efforts for standardization, is interaction-based and to some extent subjective and difficult to reproduce. And in practice, this leads to, this is empirically estimated, this can lead to up to 40% of misdiagnosis. And if the diagnosis is wrong, maybe also the therapeutic decisions would be wrong. So in the last decade, researchers in the field of cognitive neurology have resorted to neuroimaging techniques, notably fMRI or electrophysiological techniques like electroencephalogram, to obtain objective biomarkers of states of consciousness to supplement the diagnostic process or also eventually replace it. And in that context, the electroencephalogram is a particularly promising methodology as it is comparably cheap, and it can be operated in a wide range of circumstances, like at the bedside or at home. And it gives access to brain waves and other signals that emanate from neuronal activity and allows researchers to track cognitive processes in real time. The problem, however, with EEG-based biomarkers is that different research teams and different hospitals propose different kind of biomarkers. So this has led to a situation where inconsistent standards are applied, different kind of research cultures are reinforced in different institutes, and that makes it particularly difficult to pool data across several hospitals. Okay. So the question is, how can we integrate different biomarkers and how can we combine them into a robust machine learning approach? This is where our work kicks in, and I'm going to present to you essential results and concepts from the study that was just published a couple of weeks ago in Brain. And as I said, this was an extensive research project with more than 10 co-authors. And it took us a few years to make all this happen, because this is also so far, now don't start laughing, in the world of cognitive neurology, having a few hundred of these patients in a consistently tractable way is a big thing. Yeah. So this is the so far biggest study on disorders of consciousness, with more than 300 EEG recordings from different patients, and interestingly also from different hospitals. So this was quite a large-scale collaboration, not only with the hospital, with the Salpêtrière Hospital here in Paris, but also the team of Stephen Lauries in Liège. So let's have a look at the problem setting. Different biomarkers that are used in the field of cognitive neurology come from different practical or theoretical traditions. As I mentioned, so we have very classical things that are close to the observations, like alpha frequency band rhythms. So these are periodic signals that you find in the EEG or in the MEG, and that burst around 10 Hertz. They are visible to the human eye and have been part of the neurological repertoire for many, many years. But we also have specific biomarkers that were designed and that can be accessed by experimental protocols and specific stimulations that tap into cognitive science theories, like the global neuronal workspace theory. So what we did here essentially is to pool all these different markers that have been described in the literature and combine them using a machine learning approach. While this has been done already by colleagues in the past, an open question in this work was, how really are those EEG-based biomarkers really? Because as I said before, when pooling data across research groups and contexts, there is a problem that people use different EEG configurations with different sensors, different protocols for observing the EEG data. And what happens, do the numbers make sense? Are the learned functions comparable? Can we really generalize between different hospitals, different EEG protocols? To investigate these questions, we essentially had the chance to work on the Paris database of EEG recordings, but also the data from Liège, which allowed us to assess the generalization once the model was fitted on the Paris data. And specifically, we also investigated the impact of the spatial sampling and of the length of the recording used for extracting the features. One important finding, before I delve into the finding, I want to highlight the machine learning strategy that we employed here. So the tool of interest that became one of our favorite tools here are essentially random forests. Here we use a specific updated, more modern version of the random forest, which is the extra trees. And you can just think of it as a random forest with extra randomization that replaces the bootstrap over the samples when building the trees, with the total randomization of the split points. And the nice thing is, like in decision trees, you can learn any sort of nonlinear function. They are non-parametric, and the randomization and aggregation over many trees prevents overfitting. And it turns out, one thing that we did here to really also compare the impact of univariate versus multivariate approaches was to not only use a random forest with all biomarkers, but also build several random forests that use only a single variable. Yeah, so we have the same processing, we have the same feature, but we send a single feature at a time into the random forest to have a fair comparison against the multivariate model. Because in practice, one question is also, how many features should I actually extract? And there is much more human processing time if we have to extract hundreds of features. And what we can see here is that I call those univariate forests because they use one variable. So you see the distribution of a cross-validation performance over different variables. And you see that there is quite some fluctuation here. When we use the multivariate, what we call for referencing DOC forests, so don't get me wrong, this is not a new algorithm, it's a recipe. We use existing classical machine learning techniques with domain-specific feature engineering, and we call it DOC forest, DOC for disorders of consciousness, and we call it that way to be identifiable and reusable. And we see that the performance error is essentially bounded when using the multivariate strategy. Now, you may say that this is not a great performance because these AOC scores, they are essentially somewhere between 0.7 and 0.8. One important thing, keep in mind that we have label noise here. The diagnosis, our target here is the diagnosis. So if the diagnostic information is not precise, we also have a bound of our performance. And as today, we do not have yet a database or the data where we could look at other clinical endpoints like prognosis in such a rich and extensive way. We kept the target fixed on the diagnosis, but instead of looking at that, instead of looking at boosting the performance, which is difficult in the setting, we actually looked at the robustness, which is an important target of the study. And what we can see here now, if we break down these experiments and look at the behavior of the cross-validation performance across different EEG configurations, for example, only 1% of the time that was recorded went into the feature extraction versus full 12 minutes or 30 minutes. And we also have different numbers of sensors used. And the good news is that already when using 16 sensors, and yeah, something like a few tenths of seconds of the data, we are getting quite close to the reference findings that can be found in the community. And this effect is actually, I want to say something about that later. First of all, this gives us a certain robustness, and this robustness can be found again when looking at the generalization findings. So what you see here is actually a cross-site and cross-protocol generalization at the same time. So we train the data, we train the model on the Paris EEG data that comes from an active stimulation protocol that essentially exploits surprise and auditory novelty. And we apply model to EEG data that comes from resting state, where there weren't any specific instructions or no specific fluctuations, no specific stimulations. Obtained from a different intensive care unit in a different city in a different country. Okay, and what we see here is that the full-blown multivariate dog forest essentially performs as well as it performs on the training data in Paris when using cross-validation. So there doesn't seem to be any specific loss. Second, we selected, based on the training data, on the cross-validation results, the 3 best univariate dog forests. And it turns out that the markers that are most performing on the training data are alpha band average fluctuations and different characteristics of theta band oscillations. And it turns out that there is always a leading advantage. It may not be significant statistically, but there is in fact a leading advantage of the multivariate method compared to the univariate methods. And this advantage is getting actually even more enhanced when considering another computational experiment in which we train the model on different configurations of the EEG and evaluate it on different configurations of the EEG. So we had configurations ranging from 8 sensors to 256 sensors, and so on. Now what we can do is we can emulate a situation where, say, we train the model on 8 sensors and evaluate it on data with 256 sensors. And we do that for all the configuration. It's like a Cartesian product. So you make all the configurations, and those performance results actually make up the histogram here. And you can see now that the multivariate model even pays off more clearly than the univariate model. And second, as I very much like to think about the evaluation task and the profiling task in machine learning along the lines of experimental science and empirical science, it's not enough for me to just see the performance. I'm really interested in how the model behaves when I degrade the data somehow. And on the left side, we essentially do something very, very simple. We just keep adding uncorrelated noise to the test set up to a point where things break down. And you can see these different lines. Color codes are as before. You can see essentially that the univariate models are dying somewhere in terms of performance once the noise is 100 times louder than the signal, while the multivariate model is still running until it also eventually drops out at a noise-to-signal ratio of 1,000. Okay. What is interesting here is that if you only look in terms of performance, you could get the same job done with a logistic regression or with an SVM. But this aspect of robustness to noise is something that you get by using a non-parametric model that is not global and that can deal in a more flexible way with changes on a single variable. Second, we talked about the label noise. And another computational stress test that we considered is this one here, in which we, in several random draws, swap the diagnosis. And you can essentially see that if you're going up to 25–30%, there is a plateau in the performance, suggesting that we are replacing some information with other information. And at the end of the day, yeah, we roughly get the same result. At a certain point, yeah, we are replacing, we are swapping all the diagnostic labels. And if we finish the job, then we are just inverting the prediction in the end. Yeah. But what is interesting here is that we have a plateau phase, yeah, which probably is an empirical estimate of the label noise. Then I just want to highlight the work by Gilles Loup, who at the time when we met, yeah, was doing his postdoc at CERN and now is a professor at the University of Liège. And he had this NIPS paper on on better understanding variable importances in random forests. Actually, he did his entire PhD on random forests. And one thing that I learned from Gilles is that there is a problem in random forests that's related to the interpretation of variable importances. You can find masking. There is not really a guarantee that a marker or a variable that is marked as important is actually important, or that you found all the important markers. So what Gilles developed in this contribution is a mathematical proof that in a fully randomized tree, only the important markers are important and the unimportant markers are not marked as unimportant. And good news is that you can actually approximate that one by using more randomization, for example, by switching from a random forest to extremely randomized trees, and by following another set of recipes. For example, just using one variable for finding the split points. What you then get is a tree building that is independent of your data in a sense. And when you use entropy as an impurity criterion, then you actually get something that approximates a conditional mutual information measure. So we collaborated together in this paper on the interpretation of the model, because one important aspect in medicine is that you try as much as you can to unbox your predictive model, not only with sensitivity analysis as presented now, but also by inspection of parameters or importance scores. And what we found, thanks to this fine-grained mathematical and theory or interpretation, is that as a consequence of this framework, you can say that markers that have similar importance are in a sense carrying independent information. Because otherwise one of them would be high and the other one would be low. And what you see here is actually a comparison of the variable importance in the multivariate model against the univariate performance. One observation that we can make is that there are many markers that are not extremely important, and that there are a few markers that are driving the thing. But essentially that there are no big surprises. So you don't find that markers that are extremely important for the random forests are not at all informative univariately. Yeah. We essentially find that dynamics in the alpha band range and in the theta band range below 10 Hertz carry independent information and are most informative for our model. I want to briefly also highlight the infrastructure, the computational infrastructure that we exploited here. So the biomarker extraction code is now publicly accessible on GitHub. And this has been a long development over the last years. Actually, we do have a system that is currently used in the intensive care unit at the Salpêtrière Hospital in the team of Lionel Nakache, that allows clinicians to drop their EEG recordings and let the modeling run and predict, given the model, the probability of a patient of having a certain diagnosis. And then the system generates HTML reports, and it can run on Amazon Web Services or on local computers. And the good news is that all is based on Python and open source software, and notably the MNE Python software, which I've been developing together with many other contributors over the last 6 years, and scikit-learn, which you may know should you have ever worked on machine learning using Python. Second, as a byproduct of this work, we can say that we also developed machine learning-based algorithms for automatically processing EEG data and cleaning them. I don't want to go too deep into details, but there is our GitHub repository with examples. It's called AutoReject, And we have a neuroimage paper that was published last year. And it does quite a good job that we validated on more than 200 different EEG data sets and MEG data sets, and automatically interpolating data and finding bad segments and making a decision on whether the data can be repaired in a given time window or whether it has to be dropped. Yeah, last but not least, I think it's last. There is also some satellite project that co-evolved together with this work with my collaborator Daniel Lubstock. We recently actually looked at the dilemma. So when I was earlier saying that unsurprisingly, or perhaps not so unsurprisingly, the most important markers are also univariately important. And this is not always the case. Yeah. So we did extensive simulations and looked at different data sets. And it turns out actually that there are many settings, mostly related to model violations and ground truth, that lead to a situation where there are predictive markers that don't appear as extremely significant based on conventional null hypothesis testing, or the other way around. And one conclusion is that even if in your field, it seems to be the case that the more important variables are also clearly marginally or univariately important, that must not be so. Yeah? It's just in this case, the fact, good news, that the most simple markers are most robust. And finally, if you're interested in the clinical neuroscience background, there is a nice discussion article that was published together with our paper, discussing our paper by Rodika Sokolyuk and Damian Cruz from the University of Birmingham. And finally, just a few credits. All this work wouldn't have been possible without my collaborators, notably my principal collaborator in Action, Federico Raimondo, our clinical collaborators, notably Lionel Nakache, Benjamin Roro, and Stephen Laurie and his team in Liège, and on the neuroscience side here in Paris, Jacobo Sid and Stanislas Dehaene. And that's it.
Ok, merci. Question pour Denise? Bien, il y a plus difficile. Donc, ouais, je vais la poser, en fait. C'est la question qu'il faut poser. Donc, tu es en train de me dire, en fait, qu'il y avait des diagnostics qui étaient un peu différents d'un hôpital à un autre. 32 nouvelles. Et en fait, tu parlais de 40% de misdiagnosis. Je pense que c'est...
The microphone doesn't like your question.
Ouais, c'est ça. Et donc, la question, c'est est-ce qu'on prenait spécifiquement les mauvaises actions dans le passé? Comment ça se... C'est quoi ces 40%? Attends, on va arrêter ce micro. Et
je vais prendre ça.
Je crois qu'il faut couper. Si j'ai coupé celui-là.
C'est pas grave. Je peux prendre ce micro-là. I will actually respond in English. I think we should have the discussion also in English if possible. There are a few people who cannot follow us otherwise.
Why don't you ask the question in English?
Okay, so that's a good working memory test.
So the question being that you were talking about 40% of misdiagnosis. What does it mean in terms of life and death type of situations? And what does it mean? I mean, it looks to me like there is no truth table of sorts. You don't know if the person is dead, if that person is dead, or you know where I'm getting.
Yeah. That's a very good question. I think it's also a tough question. So I thought about that for a long time, and the thoughts aren't over. But one way you have to think about these labels are that they are temporal in the sense that you repeatedly interact with the patient.
Okay.
Different doctors do, and each time you do an assessment and you're integrating those assessments, and it can be that you realize the other day that the diagnosis actually changes.
Okay.
And there's a second topic, which is the prognosis. So people can change also in the sense of cure. They can improve over time.
Okay.
And the initial diagnosis that seems robust is not always a good predictor for what's going to happen.
I see.
And that makes it difficult. And there's currently, I think, no solution to this problem. So we don't have the true labels. And the labels that we have are noisy, and we have to work with that somehow.
Okay.
And my conjecture would be that in a few years from now, we may have other more objective clinical endpoints And we may also have the data then. I mean, they exist already, but they are not always centralized, and the data is somewhere but not numerically available.
Okay. So it's a life and death database that we need. Okay. Any other questions for Dennis? Il y en a deux. Tu y vas? Oh, oui, déjà une.
The question is that if the goal is to detect the consciousness state of a human, maybe we can just observe conscious people when he falling asleep. Then one can distinguish the dreaming state and unconscious deep sleep state, and we can awake him to detect the consciousness state. So did you do this kind of experiment?
Yeah, I would say that this is a very interesting direction, and we are currently working on projects in which we explicitly consider sleep. So the good news, contrary to disorders of consciousness, sleep are actually a well-posed machine learning problem, sleep data, because they are nicely labeled. There are plenty of them, and there is little ambiguity and high trust in the labels, because they're really trained experts who are really good at sleep scoring. And when you look at the recent evolution in machine learning approaches to sleep scoring, you can also see that that works quite nicely. Big challenge is that the physiology is still different, so it's not just a change. It's not a monolithic thing. There are certain characteristics that go along with consciousness. So in the awareness, we have a strong predominance of alpha band oscillations, which is fading out as we lose consciousness, but still the spatial patterns and other aspects of the signal may be different. So it's an open question that we are also trying to figure out now, to which extent we can actually use different descriptors of consciousness in different contexts, like anesthesia, sleep, and disorders of consciousness. And then the question, what kind of modeling it takes to harmonize that.
Question here.
Yeah. First, thank you very much for the presentation and giving all those results. Just a small comment. I have seen that I observed on the picture where you show that 16 sensors were enough for reasonably good results. How do you explain that with 128 sensors you get better than with 256? So is it just based on the sensitivity of how you position those sensors? Or is there any other explanation?
Yeah, so first of all, I think you see that there's quite some noise, and I did not say that there is a fully parametric, clear, noise-free effect here. So it's not that everything just gets better. You see there is some crossing, there's quite some variability also in the CV scores. So one should not interpret too much these small differences. Second, the bigger picture, how it can be theoretically possible that using fewer sensors can actually be better. And actually we see that in the supplementary findings when unboxing cases like this here. And you wonder what's happening here. So we have a generalization finding that gets much better than the baseline finding. It turns out apparently that some sensor configurations can be better than others because they give a better spatial sampling of the most important markers. And if you think about the spatial patterns governing alpha band oscillations that matter here, it can actually be a good idea to have fewer sensors because the interesting things aren't happening in the periphery. Thing that I hadn't time to talk about is that also here we use a very brutal way of getting our features. So maybe you may have had the question during the talk how we can at all go from fewer sensors to more sensors. The reason is that we are aggregating the information over the sensors and over the time by computing for each marker different features based on the standard deviation and the mean. And the reason why we do that here is that indeed in changes of consciousness, you have changes in the global statistics. So this is different from other cognitive tasks where fine-grained spatial pattern changes, but the overall power of the signal doesn't change. We do this simple approach to feature extraction here because we really have the global change in the power. Yeah.
One question here, and then
I want to know how you distinguish the locating central patient and normal people, because you mentioned in your paper theta theta band signals reflect more memory process, and alpha band power reflect a global arousal level. So from my point of view, these two markers may not be able to distinguish locked-in syndrome from normal people.
Yeah, that's a good question. So one important thing is that the locked-in syndrome is not what we looked at here. Yeah, locked-in syndrome is someone who is in paralysis and who is fully intact in terms of consciousness. He doesn't have a mental disorder or anything else. He just cannot move his body. So probably the people with locked-in syndrome, they would just have signatures that look quite similar to the controls, to the normal healthy controls. And plus, less noisy signals because you don't have motor artifacts and muscular artifacts.
You mentioned also for EEG recording, to have a promising result, we have at least 30 seconds.
So during this 30 seconds, for normal people, there must be more behavioral artifact like eye blinkings comparing to the locked-in syndrome people.
So you were asking about the data quality and
my
short data segments.
Is that in your pre-processing, maybe you didn't remove out all the artifacts.
I don't quite understand how you come to that conclusion or to that conjecture. But the claim I think that we made in the paper is that it's not about the total length of the recording. The question is how many seconds clean EEG signals do you need?
Yeah.
And we use artifact rejection procedures, so the signals that we actually fed into the feature extraction were approximately clean. And actually the trend is inverted also in a sense, because it turns out that in these clinical recordings you have lots of artifacts. And one thing, I did not dive too deeply into it, but contrary to your bias or intuition, the patients who suffer from disorders of consciousness, they move quite a lot. They do lots of things, actually. So even the patients falling into the category of the vegetative state, so to say, they can have their eyes open, they respond to stimulation, but they have no signs of awareness. Actually, for me, that was quite a shocking moment when I saw for the first time these clinical EEG recordings. I realized that the things that I learned based on MEG, magnetoencephalography from experimental data, the habits didn't work. So we couldn't use the same cleaning procedures. This is why we developed auto-reject and some more heavy-duty machine learning to clean the signals.
So I'm not a doctor, so this might be a very dumb question, but you mentioned a lot of the misdiagnosis that's going on, and I'm assuming that disorders of consciousness often have to do with a lot of brain trauma. So have you considered, instead of using just the labeled data from the diagnosis reports, also using other sources of information like fMRIs?
There is ongoing work. I mean, not on my side, but on my colleague's side. But I think we are historically a bit early. So there are different modalities, and some of them are actually extremely useful. And there are cases in which there's actually disagreement between modalities or between the doctor's diagnosis and what the modality tells you, like fMRI or PET. And we actually had available data from 2 patients that were labeled by the doctor as vegetative, but that showed activity in the fMRI suggesting active mental states, people doing something in their minds. And our EEG-based diagnosis, the model actually predicted those to have a higher level of consciousness. So they predicted the opposite diagnosis.
Ok. Donc, on remercie Denis. Alors, je ne pensais pas la faire celle-là, mais we saw Pierre-Yves talk about the early stage of learning when you were a kid, we just talked about kind of like the end of life type of thing. And in the middle, there is the coding part of things. And Iso's going to be talking to us about the coding part of things. Iso, it's your show.
So thank you very much. So I really wish I would have come today with some of the cool stuff we're doing in reinforcement learning or other things actually after seeing these talks. But what I'll be talking about a little bit today is a relatively new field, perfect, which essentially has been labeled as machine learning on source code. And it starts from a very simple premise. We have this beautiful data set that doesn't have a lot of the noisy issues that we have in all the other data sets that we've seen today, and it's source code. Right? Source code has been written by us developers. It is in very small defined languages. You know, most languages will have less than 40 tokens, and within those 40 tokens, we managed to create software that has incredible abilities. And so one of the things I'll be talking a little bit about today is, you know, how do you end up learning from large-scale source code as a data set? So we've gone in this world over the last kind of couple of decades of code bases that continuously get larger and larger, right? We have our Adobe Photoshop with 128,000 lines of code. We have our first, you know, version of Windows NT with 4.5 million lines of code. And we see this progressively going up with OpenOffice being at 9 million, Chrome that we all use at 18 million, Go code base 45 million, and then you have Google, which is arguably one of the largest code bases today in the world at over 1 billion lines of code. But where it gets very interesting is actually when we look at the developer tooling that we have created over the last kind of 30 years. And every single piece of developer tooling that we use today to do any form of understanding of source code or to make our editor smarter is rule-based. Most of us here have been active in machine learning for years, but all the tools that we're using ourselves are still fundamentally rule-based. And we haven't really actively looked at source code as this data set and at developer tooling as something that doesn't actually have to use rules. And so today I'll be talking a little bit about, you know, what does that look like? How can you enter into this field? Hopefully inspire a few people here to try to start working on some of these data sets. But before I do so, when I talk about developer tooling, I'm talking about some of the things that, you know, we touch upon GitHub or in our editor. But I can go all the way down to our compiler where, you know, rules are being used to optimize things and start thinking about, you know, how can I use machine learning to do this better? And for me, one of the most fun experiments that we did a couple of years ago, when someone new joins our machine learning team, we say, you know, what is the craziest thing you can think of that you want to try? And, you know, first couple of weeks, just go ahead and try it. And we had this researcher who's still with us, Igor, and Igor said, you know, at the end of the day, the way we allocate memory as developers feels pretty dumb, right? Like, I mean, we're making some guesses based on what we know about the data structures we're creating on how much memory this program is going to need, right? And for those of you who are, you know, still writing in C or other languages, you know, you're used to your malloc statements. And we said, well, if we look at how we predict memory, why can't a machine learning model predict memory actually for us? So we did a very, very simple experiment. We took a popular open source video game, and we took all of the memory allocation statements and we just logged it. We literally just said, okay, let's log how much memory the developer says should be allocated, and let's go and play these video games and let's see how much memory is actually used, right? Essentially a prediction of state in terms of memory. And as we started doing this, we realized early on that, okay, now we have, you know, a simple data set, literally log files. Let's just take a simple LSTM model and try to start predicting memory and overriding the malloc function in this code and actually asking the neural net model to actually predict how much memory should be used. We ended up getting a 20% increase in efficiency of memory on that video game. For those of you who've ever worked on compilers, getting a 1% or 2% in your lifetime already feels like a major achievement. And we never ended up doing anything further with this work. We don't productize things on compilers, but it's just to show you the amount of low-hanging fruit that there still is, all the way from the compiler to the, you know, the tools that you use in your editor once you start actually going away from some of the rule-based systems that we've built. So our premise is machine learning on source code will start changing the way we write code, the way we review code, the way we edit code, the way we find security vulnerabilities, and in my personal opinion, even the way that we actually end up designing programming languages over the coming decades. And so let me tell you a little bit about myself. My name is Iso. I'm one of the co-founders of Sourced. I'm a massive computer geek. I was very lucky to get into programming when I was 10
when a kid in my high school was writing an operating system in assembly but refused to write the drivers. And his strategy was to teach me how to write assembly so I could help him write screen drivers and printer drivers and things like that. I can't write a line of assembly anymore today. If you find me coding when I'm rested, you'll find me coding in Haskell. When you find me coding when I'm exhausted, you'll find me coding in Go. For those of you who have worked in functional programming will understand that. And I'm interested in a lot more different areas. Here are some of the ones that are mentioned. So I'll be talking a little bit about machine learning on code, giving you a few pointers of what's interesting research being done today, some use cases, and a little bit of my opinions on the future. So at the end of the day, when you look at ML on code, there's a lot of adjacent fields in machine learning from which you're going to draw inspiration. And probably the most prominent one is natural language processing. Right, at the end of the day, all of the issues that you find in doing NLP work, of the ambiguity of languages and noisiness of your data set, and just the fact of the complexity of language, you don't find in programming languages. You don't find in source code. You think. And I'll talk to you a little bit about why you think. If you take any big code base or even a small piece of code, and you start looking how much of source code is actually natural language, well, the majority of it is. Right? A programming language will have 40 to 100 tokens. But at the end of the day, we manage in source code to use natural language everywhere to signal intent. I'm connecting to a database. I'm having a credit card number value here, et cetera, et cetera. Actually, so interesting. So we run a data pipeline, actually in a physical data center here in Paris, that indexes all of the world's public Git repositories. We're talking close to 80 million Git repositories, about 350 terabytes of compressed data. And essentially, if you've pushed it to GitHub or a self-hosted cgit server and it's public, we will have it. And so we like to play experiments with this data and run big data pipelines. And one of the first things we did is, okay, let's try to figure out all the natural language that actually is being used, all the identifiers, let's extract them. Let's go through that data cleaning process, because as developers, we write variable names in all lowercase and lots of different cases and lots of issues. And once you go through that cleaning process, you end up with about 2 million unique names and tokens, right? And 2 million meaning that when you have foo bar, it's actually foo is one token and bar is the other, no matter if it's all lowercase. That is about a magnitude larger of that natural language that we find in the Oxford English Dictionary. And most of this actually is English language tokens. So as developers, we get incredibly creative about how we name things in source code. And then one of my personal favorite fields, and where a lot of our work at Source is based on, is everything over graph-based data structures. And I'll talk a little bit today about why that matters so much. And yeah, lots and lots of data. So here are two interesting data sets that are worth having a look at if you're interested to get into this field. One is public Git archive hosted by us. It's essentially every Git repository with more than 50 stars, fully cleaned with all of its forks and duplicates. The other is the GitHub archive, which is a URL pointing data set to other GitHub projects. So at the end of the day, there's a lot of tasks that you have to go through. And I won't go through all of these today, but at the end, your data pipeline starts looking from, the first question is, do I want to evaluate source code as a file at its latest version? Or do I want to learn from how code has evolved over time, commit to commit? For anyone interested in doing research in the area, a big hint, the most interesting stuff is learning how source code actually evolves over time. We introduce bugs, we remove bugs. We have different actors upon the same pieces of code. We rename things, we change things. And all of a sudden, you have this beautiful data set where you actually have everything tracked of how it's evolved over time, and you can start doing interesting things with it. So we have an engine. It's actually part of what we deliver as an enterprise product to big companies that want to do analysis over their source code. And essentially, if I want to extract all the functions from 1 million Git repositories or 100,000 Git repositories, I write a statement like this, right? I select all my files from my version control system, and then I say, okay, give me a universal AST. I'll talk a little bit about what that means, and now extract me all the functions. The thing is, though, when I look at source code, there's lots of different ways of looking at source code, right? I can look at it as a compiled binary. I can look at it actually as what every single token means, right? What is an identifier and what is a string and what is a function definition? But in the end, source code, when it comes to the compiler, is viewed as an abstract syntax tree, right? A tree that actually represents source code, similar to how we have a decision tree in a model. But more so than that, it actually ends up having different representations. I can have a control flow graph of how actually things happen. I can have a data flow graph. When I look at source code today, it depends on lots of libraries, right? When you're writing your random forest models, you're using scikit-learn and other such things. So all of a sudden, you don't just have the source code, but you have this massive dependency graph around it. So at the end of the day, you end up with lots and lots of graph representations of data. Your call graph, your data flow graph, your dependency graph. And so early on, we said it'd be really cool to take this data set, build a clean data set of it, and start applying some of the graph-based neural network techniques, other type network techniques, to this, right? What can we learn from the world's source code? And I talk a lot about neural nets, but in the end, we use a lot of things as well, like decision tree models, localized sensitive hashing for cleaning our data, etc. But at the end of the day, we all know that really running things at scale is usually some version of a bunch of embedding models, a bunch of cool neural nets, a bunch of hash tables, and to make things actually fast. So one of the first things that I would really like everyone to walk away with here today is when you're looking at source code and you're looking to understand it, in our opinion, there's really three axes of which to look at a piece of code. The first is its structure, right? How do we actually structure what we're trying to do, which is the how do we do something. The other is the actual natural language, right? What are we intending to do here, right? When I say connect to a database, I know exactly what's going on. But when I show that same piece of code with all the variable and identifier names, change to A, B, C, and D, I have no more idea of what's actually happening. And the other is style. And style really comes from the fact of when I look at natural language and I look at a piece written by Mark Twain, and I look at a piece written by Shakespeare and God forbid Malcolm Gladwell, everyone will argue that all these three of them are great authors or not. And so as we argue this, we don't really have an objective measure of what is good or what is bad. And in our opinion, when you talk about source code, you can't have an objective opinion either of what is good or what is bad. At the end of the day, it is highly subjective of how we write source code. When I write my Haskell, I will do certain things because they indent nicer. It's my little OCD on my code that I love to do certain things, not because it's more performant or because it optimizes better, but just because it feels right to me. And this is why we have so many debates in the programming language communities of how things should be. And that's why certain people like their curly brackets and other people don't. And so one of the first premises for us was, can we understand similarity in source code across these axes? Because when you have these large data sets of, hundreds of terabytes of data, at the end of the day, they're not very useful, right? At the end of the day, data becomes useful when I actually start being able to say, okay, what is all the source code related to encryption? Or can I look at this function and all the functions that are similar trying to do the same thing? Because then all of a sudden I can build possible program spaces that do the actual same action. And so similarity at the end of the day for us often ends up being solved by big embedding models. There's a lot of different approaches that we've taken. And if anyone's interested, ping me. We have really learned embeddings at scale. And the fact that, your classic Word to Vex aren't going to work at large scale. And there's a lot of interesting stuff to talk about there. Right, and then I mentioned earlier the fact that as developers, we are great at not actually using conventions, like separating things out in casing. And there's some interesting, very, very simple applications that you can do today with basic character-based neural network models or BIOS-TMs that all of a sudden start now understanding, hey, this is how it should be written. But the really, really cool stuff, in my opinion, is when you start dealing with source code as graphs. And when you start actually learning from those graphs and being able to do things like, okay, here I have a piece of code. And at the end of the day, here I see a clear pattern as a human. I'm initiating from here, opening a file, and I'm closing this file. Here I'm opening another file called 2, and I'm going to close that file, right? And pretty much anybody here can look at that and say, okay, what should be here is actually the closing of the file that I just opened, which is represented as a graph in the data structure below. These are the kind of things today that are already very feasible to actually predict. And if you look at this and you work in different fields, such as protein folding or others, you'll start seeing the exact same kind of techniques that can apply. Because at the end of the day, it's a graph and you're trying to predict something that should be a node in a graph. There are some other really cool things around large-scale embeddings and large-scale vectors for actually showing representation of source code that aren't just dependent on the language, but taking regard to structure. This is a really nice paper by Uri Alon out of Israel, where they did some really cool work on actually building, based on the AST and the graph, structural embeddings, and then using those structural embeddings to start predicting functions and names that should be where. And I'll jump a little bit over this for sake of time. But what I really wanted to leave you with here today in the 15 minutes I had was there's so many areas today where we have used graph-based data structures, where we have found incredible techniques, neural network-based or non-neural network-based, that are able to do things like predictions. And we have not yet applied them to source code. There's a massive field of things that we can be doing around bug detection and prediction. We're doing a lot of stuff around learning from the history of code over time of how it changes. So we look at how this graph evolves over time, commit to commit. And on aggregate, on large data set, we introduce a lot of bugs as developers, but we also remove a lot of those bugs and fix them, right? So are we able to actually learn from this large data set? Learning a style in a code base, right? There's a lot of stylistic things that we do as developers that we'd like to have consistent. Can we learn those? We actually have a style analyzers being released at the end of this month. They can go into a code base, learn its style, and actually afterwards automatically tell developers like, hey, here you should be doing X, Y, or Z because that's the common style of this project. And then there's the cool futuristic stuff, which mainly falls in the realm of program synthesis. For those of you who have done any program synthesis work or research, till date, it's been very academic toy example. We have a little language, like a subset of Prolog, and we have a well-defined set of inputs and outputs. We're going to generate the whole program space, and we're going to find some way to go through that program space and determine what can match from these inputs to outputs. And that for the last 40 years hasn't really gone past the realm of academic examples because we're using artificially generated data sets of inputs and outputs. And we're not actually using real-world knowledge about how we program. So one of the coolest things, in my opinion, that the future is going to bring is that we have these massive data sets of how developers have solved certain tasks. We have massive data sets of mapping inputs to outputs, right? That's unit tests that we've written. I'm introducing this, and I'm expecting, X, Y, or Z. Why can't we actually be learning from those real-world data sets and applying those to actually program synthesis challenges, right? And taking that beyond just what Excel is able to do today. And as a developer, I can just write my test of this is my expected input, this is my expected outputs, and have code actually being suggested to me. So we have this collection that has now become quite active in the community, that anybody who's doing any research in machine learning on code lists their paper here. So there's about 300-400 papers here at the moment. You'll see that most of them have actually come up in the last 3 to 4 years. When we started as a company about 4 years ago, there were a couple of dozen papers. Today, that's gladly become a bigger community. So this is a really good starting point where also papers are specifically marked for beginners in the field. And just to kind of preempt this question of will developers be replaced, right? Can we get to the world of there are no developers? I absolutely do not believe so, just from the premise that writing source code is only a small part of the developer's job. At the end of the day, we're solving problems, we're looking for architectures, we're trying to come up with solutions, and code is just a way for us to actually implement those solutions. So I think a lot of the routine things that we do about writing code can be made a lot better and can be assisted, and in even many cases can be written for us. The actual act of software engineering and solving problems in itself will only go away if we ever crack AGI. And you might have seen, I consider neural networks dumb pattern matching machines. So I'm highly skeptical in that field. So thank you very much.
Any questions for Ison? Yeah.
Your ideas are very reminiscent of Eric Meyer idea on language evolution. And so, do you have any thoughts on this kind of evolution? So, developer won't be replaced, but how? What's the divide? About problem solving, data analysis, and delivering solution at scale.
Yeah, so Eric Meyer recently joined a group at Facebook where they just released something called AutoFix, where they're actually detecting bugs and automatically fixing bugs in the Facebook code base. And I'm a big fan of Eric, hence because of his Haskell background of the University of Utrecht. How I look at it is that, and it's maybe a very simplistic way, when I write code, there are parts where I'm bored. And there are parts where I'm bored because I'm doing routine things. I'm doing things that I absolutely already know how to do, right? And that can be the cleaning or transformation of data, where if I could have written a sample of how I want my data to look like, that would have been very quick. It has to do with parts where I am introducing code I've written dozens of times before because I'm connecting to a database and I'm doing some simple extraction. But when I'm not writing code and actually sitting down and trying to figure out the architecture or the solution to a problem, that's where I believe we're going to have the hardest time of actually automating things. Because when we start coming into what's the interface then between the system and the human, right? It's going to be some form, and then we say, it's natural language. I will go and describe to you what I want my application to do or what I want my backend system to request. And the moment you go down that route, you end up creating a programming language, right? Programming languages are just there to essentially narrow the scope of what we're able to say to do X, Y, or Z. And so what I personally believe is that the style of programming languages and the complexities of them will go away. I personally actually think that the way you'll see your code in 10, 15 years, I can have the same piece of code and all of us can adapt it to our own style. The underlying data structure will be the same. I personally believe that, opening a file can be something that can be described in a much better way than having to know what library or package is needed to open a file or to read, byte by byte. But I don't believe in full natural language interfaces because natural language is too messy and too ambiguous.
Okay. Yeah.
Hi, I like the talk a lot. I just have an open kind of critical question. So with software engineering, most of the times we ignore the hardware on which the software works. So when you do models like this, how do you actually adapt to hardware that changes? I'm running a nice CPU, I'm running a nice GPU, I'm running a nice TPU, running a nice OPU. Yeah. So,
well, I think at the end of the day, the level that we're doing analysis at is at the source code level. So we get to completely ignore what the underlying hardware is. Is it interesting to start applying this work at a much lower level part of the system? Absolutely. And at the end of the day, there's a massive amount of signal there that you can use. And it doesn't even have to be about between a CPU or the GPU. It can just be on different architectures, right? Intel versus ARM. We haven't touched any of that work. There is some very, very cool work being done in an adjacent field of kind of reverse engineering malware. And there, when you actually start looking at the techniques that people are using there, you can very easily imagine that actually being related to the hardware that underlies it. That's kind of my own personal opinion. I am also not personally low level enough to be like saying, okay, what could you be doing at the CPU instruction level, right? When we look at some of the security vulnerabilities that came out around Intel, like those are rule-based systems. What if we actually replace those, with model type architectures? But probably that wouldn't even be performant yet today. Does that answer your question? Okay.
Any other question for Isa? Yeah.
It's not really a question, it's more a comment. I think I have a clue about why machine learning techniques didn't make their way into the programmer's world, because basically it means giving away a bit of control on your code, on your optimization techniques. And let's face it, developers are control freaks. So, well, I think that's the main reason why we haven't seen these techniques yet.
I think it's a very good comment. We personally, as a company, we do everything as assisted, like giving suggestions. We actually don't touch stuff that changes behavior without you first approving it. I think actually in reality, it might be a simpler answer. Over the years, having spent a lot of time in this field, the people who have strong machine learning backgrounds, in vast majority, don't have strong programming language, design, or compiler backgrounds. There's two very, very different worlds. And in some places where those worlds geographically combine, so I'm actually literally talking physical places, like in Moscow, and like places where a lot of the people who went into machine learning used to be from compiler backgrounds and things like that. There you actually see a lot of the work bubbling up. So I don't know, one of the places where a lot of cool things are happening is at JetBrains in St. Petersburg. And you go look at the teams that are there and you look at the backgrounds. I've been doing 6 years of machine learning, but before I was a hardcore compiler guy. And that often has a lot to do with the local engineering culture or progression of people in their career. What if I go into the UK or the US, and I look at the people who are doing machine learning backgrounds, you often won't find this very strong programming language research or compiler background itself. So I think it's also a little bit more the fact that these worlds are just starting to come together. And the places where they've more naturally come together, that's actually where we see a lot of things pop up that are actually, yeah, if you know your data and you know your problem set and you know machine learning, you're more likely to apply to it. That's, I think, might be just the easy answer to it.
Okay, the pizzas have come. So let's thank ISO once again. So the pizzas are here and the beers are here in the fridges right in front of us, right here, right? Le prochain meet-up, c'est le 12 décembre. Ce sera le 100e. Si vous avez des présentations, n'hésitez pas. Merci encore d'être venu. Et des idées. Et des suggestions. Merci encore d'être venu. Merci.